Intro to maximums and minimums. And really, actually, today we're going to be focused on finding maximums and minimums on closed intervals. But we'll get more into that. We need to first get a few new definitions here. So first of all, f of x has blank at x equals a if f of x is less than or equal to f of a for all x in the domain of f of x. So what does that mean? Well, if there is some y value here that's bigger than the rest of the other y values, we call that a maximum, okay? And if it's bigger than all the x values in the domain of f of x, we actually call it an absolute maximum. And f of x has a blank at x equals a if f of x is greater than or equal to f of a for all x in the domain of f of x. And so what should go here then is we have some y value that is smaller than all the other y values, and we'll call that the absolute minimum. Now, these next ones have a subtle difference. The inequality looks the same, the beginning looks the same, but there is this subtle difference here. One is for all x in the domain, and the other one is for all x near a. Well, when this is just when it's just bigger than all the points around it that are nearby, we call this a local maximum. And if we have a y value that's smaller than all the y values near it, we call it a local minimum. And all four of these words are considered extrema. So absolute and local minimums and maximums are referred to as extrema. All right, now that we have all these new definitions, let's see how it works. So you may notice that this graph here actually has two valleys, okay? And one is lower than the other, but note that right here, this point is smaller than all the points near it, right? So this is called a local minimum. While this other one that's lower than all the other y values, this is called an absolute minimum. Sometimes in place of the word absolute, you'll see the word global. So sometimes they'd say a global minimum. And then lastly, we have some maximums to think about. You can see we have a point here that is a local maximum. Right? It's larger than all the points around it. Okay. Nearby. Okay. And then lastly, are there or is there an absolute maximum? And the answer to that is no. This thing's going to keep going, right? It's not going to obtain some largest value here. So this one has no absolute maximum. All right, and so we have ourselves a definition here at the beginning of page 2. a blank for a function f is a value x equals a in the domain of f such that one of the following occurs. So this new word is going to be a critical number. All right, and one example of a critical number is x equals a, right? We're talking about values x equals a, such that f prime of a is equal to 0. Another one that we could look at, another type of critical number, is if f prime of a is undefined or does not exist. I'm going to say undefined. And then lastly, we could be looking at the endpoints of some closed interval. And this brings us to the closed interval test. So on a closed interval, a continuous function has an absolute extrema at a critical number. So this is nice. If you have, again, we need it to be a continuous function, at least over the interval that we're concerned with, and it needs to be a closed interval. We have those two conditions met, we will have both an absolute minimum and an absolute maximum over that interval. And here's just a really basic example of what we'd be looking at here. So if we were to restrict ourselves looking for absolute extrema just on the interval from A to B, so we could almost imagine just ignoring really the rest of this graph. And so you can see now on this interval that we're actually looking at, the largest value happened here, which is at the end point of this closed interval, one of the endpoints. And the minimum, this one occurred where the first derivative is equal to 0. Okay. So we can see that at least in this example here, that our absolute minimum, absolute maximum occurred at critical numbers.